So we are moving from manual air specification to thermodynamic reality. Today you will learn to link mass and energy enthalpy matrices, calculate oxygen demand, and prove how blast heat directly cuts the blower cost. So look at this 2500 cubic meter hearth picture. Those data stream for charge and iron are our primary balance variable. We are not just making metal, we are solving a complex chemical system. So, to understand this shift, we must look at our modeling evolution. So, the evolution towards a predictive model follow this roadmap. So, phase 1 was a static uh, mass balance where we manually specified oxygen. We are now at phase 2, that is merging mass and enthalpy. So oxygen requirement are dynamically calculated based on the internal thermal constraint. Coming to phase 3, where phase 3 remains our goal, a fully predictive digital twin. The so what factor is automating these calculations removes the human error, ensuring the furnace always maintain the exact heat needed for the steady state production. And this require a fundamental rebalancing of our mathematical matrix, and which is this rebalancing of matrix architecture is shown by the slide. Uh, so as you can see, we have swapped manual input for the thermodynamic laws. So we removed equation 4.8, the manual oxygen specification, to make room for equation 5.7, that is the enthalpy balance. So notice how the enthalpy block slides into a mass matrix. Instead of you telling the furnace what to blow, the model now tells you the required air volume to maintain that heat. So this rebalancing ensure we never underdrive the process during the thermal shift. So let's look at the engine in action using our 1200-degree baseline. So coming to the 1200 degree centigrade baseline, now we are calculating this oxygen demand. So here is our baseline engine at 1200 degree centigrade. Row 10 calculate an enthalpy term of 400 for every 1000 kg of iron. Now the matrix predict exactly 298 kg of oxygen and 1283 kg of air. So if your blower are not hitting this specific mass flow number, your thermal state is drifting. So this engine provides the precise benchmark needed to begin testing the furnace predictive limits. So let's test that power by jumping to 1300 degree blast scenario. So now coming to this testing predictive power, the 1300 degree centigrade scenario. So let's test the model. If we increase the blast temperature to 1300 degrees shown by this orange needle, how does air demand change? We keep carbon and iron output constants locked, but the thermal reality of the blast has shifted. The so what is pure efficiency. Every extra degree of heat in the blast is enthalpy. We do not have to generate by burning expensive coke. So recalculation is now mandatory. To solve this, we must update our thermodynamic input equations. So coming to our next slide, which is going to discuss exactly on the updating the thermodynamic input. So we update using these specific enthalpy formulas for oxygen and nitrogen. Notice they are the temperature dependent, measured in the megajoule per kilogram. At 1300 degrees, oxygen carries 1.352 megajoule per kg. So injecting these values into equation 5.7 recalibrate our furnace thermometer. So these account for the higher energy quality of the blast air, which fundamentally alter the internal heat balance of the matrix engine. The model's response provide a clear diagnostic comparison of efficiency gain. So now let us see about the diagnostic comparison, the model response. So look at the delta column. Increasing blast heat by 100 degrees drop our required oxygen by 6 kg and total air demand by 28 kg. So this simulation proves that hotter air demonstrably reduce the mechanical work of our blower. So for a high output furnace which saves 28 kg of air per ton translate to massive annual electricity and oxygen plant saving. So we are substituting heat for mechanical power. These inverse relationship create a clear trend line for our operational strategy. And this is the inverse relationship, that is temperature versus air demand. So these trends define our strategy. As temperature increases, oxygen and air demand drop linearly. So at 900 degrees, we need 1375 kg of air as it is clearly shown in the slide. At 1300, it down to 1255 kg. So this is your operational map. It tells you exactly how much to throttle back the blowers as stove heat rises. So without this adjustment, you risk overheating the raceway and destabilizing your chemistry. So physically this works because of the thermal seesaw inside the furnace. The thermal energy balance, that is, think of let us think of the furnace as a thermal seesaw. So sensible heat from the blast air balances the heat from the exothermic carbon oxidation. When the blast brings more enthalpy, the orange block the model lighten the oxidation side to maintain a steady state. So less required oxygen means less required oxygen in the blast air. So we are literally substituting thermal energy for chemical reactant to lower our overall fuel cost. However, we must acknowledge the current limitation of this model. That is our next slide, which is talking about the reality check, why we are only one third. So as you can see, a reality check, we are only one third of the way there. Look at the top gas temperature. It is locked at a static 130 degrees. In the real furnace, that's a dynamic dependent variable. Because we are using a false static constraint, we cannot yet fully trust the model's prediction for top line efficiency. We have mastered the furnace lungs, but we are still working on the exhaust. So despite these, our framework provides a clear path to the next frontier. So So finally, we have integrated mass and enthalpy like puzzle pieces. Oxygen is now a calculated output, providing that heat saves air. Our next frontier is unlocking the top gas temperature to create a 100% dynamic digital twin. This is the journey to a furnace that anticipates its own needs before hearth even feels a change. So let's take this logic to the